Hi, I'm Jeff Hyde from Bowdoin College in Brunswick, Maine. And today I'm going to be telling you about some work with Cyril Kraki-Sarbnowski and Mark Kamiankowski at Johns Hopkins, having to do with possible neutrino self-interactions and how they might show up in astrophysical spectra. And there are several motivations one might have for looking at something like this. One is that if there's a hypothetical, for example, let's say nu tau interaction, that's a difficult thing to constrain in a terrestrial experiment. These type of neutrino self-interactions are often considered for a variety of reasons, notably recently as proposed solution to the Hubble tension. And finally, there are a whole bunch of experiments that are existing and upcoming that will be pushing down the sensitivity to neutrinos over a range of energies, hoping to detect, for example, the diffuse supernova background, and looking at other high energy astrophysical neutrinos. So one might ask, well, what could we, based on the spectra we see, what could we learn about the properties of neutrinos? So for the purposes of this work, we're going to think about a scalar mediator, phi, and an arbitrary self-interaction matrix. So previous work that I'll talk about soon has considered neutrino self-interactions in astrophysics and cosmology, but often with a diagonal or other simplified self-interaction. All right, so the general scenario we're considering is there's some source of a primary flux, let's say neutrinos from a supernova. The neutrinos propagate to Earth, and then some flux spectrum is detected at Earth. During this propagation, the neutrino self-interactions can come into play as they potentially scatter on the cosmic neutrino background. This is a scenario that was first looked at considering supernova 1987A, passing through a certain amount of cosmic background neutrinos on its way to us. But if we're thinking about, for example, the diffuse supernova neutrino background, they would be coming from much farther away and therefore exposed to many more background neutrinos along the way. So the question we have is, how do we take some arbitrary form of this neutrino self-interaction and figure out the effect on the flux spectrum at Earth? So that's the setup. What did we do? What am I going to be telling you about? Well, we have some inputs in our model, some primary source term. So for example, supernova neutrinos or something else. And we might hypothesize some neutrino self-coupling matrix. And that depends on what model we're thinking of, what specific self-coupling matrix we might look at. The result we want is a spectrum arriving at Earth. And what we do is we give an analytic calculation, an analytic way to figure this out. And then I'm going to show you some couple of applications on top of that. But a couple of things to point out about this. One is that I'm just showing a couple of examples. There are a lot of different scenarios you can imagine this applying to. And on top of that, it's not obvious that this can be done by an analytic calculation under a few approximations. In general, and you'll see why in just a moment, this is something that you would think about doing with some sort of a Monte Carlo that takes a lot of computational time. All right, so we've got our cosmic background neutrinos just sitting here non-relativistically hanging out until some much higher energy neutrino from an astrophysical source comes in and runs into one of them. And this is an important picture to keep in mind for interpreting the spectra later. We have two outgoing neutrinos, but they'll be lower energy than the original source neutrino. And as I said, others have thought about this type of scenario before. What we're doing here is generalizing it to an arbitrary self-coupling matrix and giving a closed form solution to avoid the really time-intensive numerical part. All right, so let me describe the same thing now in equations. So in general, we want to write down some Boltzmann equations for the neutrino flux. We're thinking about this capital phi sub I here as being the flux in the ith neutrino flavor as a function of time it's observed and the energy of the neutrino that we're observing. And there's a part that comes from just the expansion, just the fact that this flux exists in an expanding universe. Then there's also the source term, so the primary flux, whether that's the supernova neutrino background or some other phenomenon that's characterized by this. And if we just had that, there would be no effect from the scattering during propagation. So we have to add a couple of more terms. First, we add this scattering term, and this is a part that just removes the initial neutrino from the spectra. So this neutrino comes in and scatters and is taken out of the initial flux at the energy it was at before, and then is added back in later. And that's what this so-called tertiary source term does. This is the one in that picture of the neutrino coming in and scattering and two neutrinos going out. This would represent adding in the two neutrinos at the lower energy. And so this is the re-injection of neutrinos after that scattering event. And both of these terms depend on the specifics of the neutrino self-interaction that we're considering. And from looking at this, we can understand why this is often done numerically. For example, this tertiary source term depends on how many scattering events happen. This depends on what the initial flux is, but this also affects the flux. And so it appears like it would be quickly intractable analytically. One approximation we can make to simplify this is resonant scattering. So we basically assume that because the cross-section is much larger near a resonance, it can be taken as a delta function. And this is often a very good approximation compared with the resolution of a detector, for example, at the resonant energy, which I just want to point out depends on what the mediator mass is. And so experiments that are sensitive to different neutrino energies will also be sensitive to resonances at different energies and therefore different mediator masses. All right, the general solution from our paper can be written down in this form, although each of these includes a whole bunch of further terms. And for those, because the details get very involved, I will just refer you to the paper for the details. But something to notice is that this term right here includes both the primary and the tertiary sources, which of course are related to each other. The rate at which tertiary neutrinos are re-injected after scattering should depend in some way on the source. And so these are coupled in some way, as well as terms here that couple different neutrino flavors together. And earlier I said, well, we have a closed form solution for this flux. How could this be a closed form solution? I'm going to answer that as we look at the first example, which is the diffuse supernova neutrino background. Okay, so what we're looking at here is the flux spectrum of neutrinos as a function of neutrino energy, collectively from all of the supernovae that are happening throughout the universe. The black curve is a prediction in the absence of neutrino self-interactions. So we just create the spectrum as a function of redshift, propagate it freely through an expanding universe, and then detect it now. And this is for a supernova temperature of 8 MeV. Qualitatively, nothing changes if you adjust the supernova temperature. Now, for comparison, we're showing two different scenarios, one where we have a tau neutrino self-interaction with this coupling strength and all other self-interactions are zero, and another where we're looking at an EV scale sterile neutrino that mixes with the active neutrinos and has the same self-coupling strength. And so these are shown by these different curves. And then this green line here just shows the threshold for inverse beta decay. So a significant difference in the spectra over here, but we're not going to see that part. So you can see that there are multiple resonant energies, and that corresponds to the fact that there are different neutrino masses, recalling that the resonant energy depended on not just the scalar mediator mass, but the neutrino mass as well. Above the highest resonant energy, there's no change in the spectrum at all. All three of these curves lie on top of each other. And that's easy to understand based on that picture I showed earlier of one neutrino coming in, scattering, and getting two neutrinos of a lower energy, because there's no resonance up here above the highest resonant energy to take a neutrino out of the spectrum. And when they come back in at a lower energy, it's lower than one of the resonant energies, so there's no effect up here. And the general trend then is scattering from the resonant energies and depositing an increase in the spectrum at lower energies. That's also the reason why the solution I just showed actually can be done in a closed form manner. The tertiary source term at a given energy, say right here, only depends on the primary source term at higher energies than that. So in other words, when evaluating this, we have to be careful about exactly what energy we're evaluating each term at. And again, details of that are in the paper, but the general trend is removing neutrinos from resonant energies, depositing them at lower energies. All right, so these spectra look nice, but what about the question of actually detecting something at some statistical significance? So that's what this addresses. And this is the positron energy produced by inverse beta decay. And this would be the number of events per 22.5 kilotons over 10 years at super K with gadolinium. And the black curve again shows the sort of mean spectrum expected for an 8 MeV supernova temperature. And then the green and red curves above and below show plus or minus 1 standard deviation, assuming Poisson statistics. And we can see that down here, we can get the tau-tau or sterile-sterile self-interaction suppressed by more than 1 sigma. What that looks like in terms of a space of parameters for this scalar mass and coupling ends up looking like this for, again, the same parameters I just showed in the previous plot. And the different masses here just correspond to different regions constrained by resonant scattering due to each mass state. Okay, another example that we looked at is high energy astrophysical neutrinos and detection at IceCube. What's shown here is neutrino energy and E squared times the flux. So we're comparing this with an E squared flux. And what we did was we took a model of using the best fit parameters to the high energy part of the spectrum observed at IceCube. So the spectral index at 2.53, and compared that with the exact same scenarios as I just showed on the previous slide for the diffuse supernova neutrino background. So looking at the black curve, which lies under here, and you can see right there being the case with no self-interactions. So we just have the spectrum purely following the e to the minus 2.53. And then in each case, we again get resonant scattering. And the effect here is really, as it was with the supernova neutrinos, much more noticeable in depletion of the spectrum at resonant energies than in any possible reinjection at lower energies. That was somewhat noticeable for the supernova neutrinos, at least down here, but in practice with the statistics hard to pick up and just not even really noticeable here at all because of how fast the spectrum is falling. But nevertheless, we can think about what constraints IceCube can put on these types of interactions. And we get something that looks like this. And just want to point out, this is in the MeV range for this meteor mass rather than KeV, which is what something like super K would see. And that again is because the resonant energy depends on the meteor mass. So because ice cubes looking at higher energy neutrinos that probes higher resonant energies and therefore higher mediator masses as well. So the takeaway points here are not just that super K or ice cube can constrain masses and couplings of mediators that couple to neutrinos, but also that these are just two examples, and our work here gives us a general way of examining the effect of neutrino self-interactions with an arbitrary self-coupling matrix and just arbitrary source, and the effect those might have on sort of spectra without a very costly numerical integration. So thank you for your attention. I'm looking forward to any questions you have on Slack or in the Q&A session, or my contact information is down here.